Hello, my name is James, and today I'm going to be going through my assignment for MATH1013, where I'm going to be proving Theorem 1 of Chapter 13 of the third edition of Calculus by Michael Spivak, more commonly known as the first fundamental theorem of calculus. So let's start off with the actual theorem. So the theorem says, we'll let f be integrable on the closed interval ab, and we define capital F on the same interval by capital Fx is defined as the integral from a to x of lower ft dt. So if lower f is continuous at c in that same interval we described earlier, then capital F is differentiable at that point, giving us the derivative of capital F at c is equal to lower fc. So now let's start with the proof of this. This proof will be split up into three cases. The first one we'll be covering is when c is equal to a. The second is when c is equal to b. And the third is when c is an element of the open interval of a to b. So let's start with case 1, shall we? So when c equals to a. So we'll start first off with the general form of the derivative. Well, since we're looking at a, we have to look precisely at the right-handed derivative in this case, because of course the derivative isn't defined on the left of a. So this of course gives us our general form of the derivative, as we can see here, also showing that h is greater than 0. And if we then use the notation we had before for capital F, we get that capital F a plus h, take capital F a, is defined as that integral. So continuing on, let's define a partition p such that p is that partition there, and it's a partition of the closed interval from a to a plus h. So with this, we can define little mh and capital MH as such, where lower mh is the infimum of f of x, for x is an element of that interval, and mh is defined the same way, but instead of infimum, we're looking at the supremum. So let's continue on. We're going to recall a theorem from Spivak that says if m is less than or equal to f of x and is less than or equal to capital M, then m times b take a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to capital M b take a. So using the integral we had before, we're going to get that mh times a plus h take a is less than or equal to that integral there, which is less than or equal to capital MH times a plus h take a. Simplifying down to lower mh times h is less than or equal to the capital M substitution we had before for that integral, which is less than or equal to capital MH times h. Now dividing both sides by h, we're going to get that lower mh is less than or equal to the fraction we have there, which is less than or equal to capital MH. Now, applying squeeze theorem, we're going to get that as a result. And the reason this works is because we know the limit as h approaches 0 from the right of lower mh is equal to the limit as h approaches 0 from the right of mh, which is just equal to fa. So, because of squeeze theorem, this gives us the result that the derivative of capital F at a is equal to lower fa. So we can say that case 1 is done. So now let's look at case 2, when c is equal to b. This is defined quite similarly, but instead of the right-handed derivative, we're looking at the left-handed derivative, since the interval isn't defined for anything greater than b. So of course, h is less than 0 in this case, and we're going to find the capital F the exact same way as we did before, with that integral there. So we're going to find the exact same partition, but the partition is now of the interval b plus h b, knowing that b plus h is on the left because h is less than 0. So we define lower mh and mh similarly, but with that same interval we just described then. So then going through the exact same motions as before, we're going to get that lower mh is less than or equal to b take h, which is less than or equal to that integral, which is less than or equal to capital MH times b take h, giving us this expression here. Of course, if we multiply both sides by negative, flipping the inequality signs, we're going to get the integral that we described earlier, which is going to give us this. It's going to give us little mh times h is greater than or equal to capital F b plus h, take capital F b, which is greater than or equal to capital mh times h. So now what we do is we divide both sides by h, but since h is less than 0, this flips the inequality sign again. So this gives us lower mh is less than or equal to that fraction there, which is less than or equal to capital mh. So now if we apply the limits again, because of squeeze theorem, and we recall that the limit as h approaches 0 from the left of lower mh is the same as the limit as h approaches 0 from the left of capital mh, which is equal to fb. So because of squeeze theorem, this gives us that the derivative of capital Fb is equal to lower fb. So that's case 2 done. So now we're on to case 3. So this is quite similar to the other two cases. We define the derivative pretty much similarly, but instead of it being from the left or the right, it's just a whole derivative, because we of course can go from the left or the right at c, since it's on the open interval. And we define our integral the exact same way, capital F c plus h take capital FC is equal to that integral. So this gives us two separate cases to look at, one where h is greater than 0 and one where h is less than 0, because of course we recall that if we take the left and the right hand derivative and they're the same, then that's going to be equivalent to the limit of the whole thing. Alright, so we'll look at when h is greater than 0 for that interval. So we're defining a partition p the exact same way as before, but this is on the interval c plus h. And then we define lower mh and capital mh the exact same way, but on that same interval. So now this is going to give us the exact same expression we had before, but instead of a, we have c. So that's going to end up giving us lower mh times h is less than or equal to capital Fc plus h, take capital Fc, which is less than or equal to capital mh times h. Dividing both sides by h, we're going to get lower mh is less than or equal to f. Well, I'm not going to say that whole thing, but you can see that there, which is less than or equal to capital mh. Squeeze theorem is being applied again to give us this. And we, of course, recall that the limit as h approaches 0 from the right of lower mh is equal to the limit as h approaches 0 from the right of capital mh, which is equal to fc. Giving us that derivative of fc is equal to that limit from the right of 0, which is equal to lower fc. So that's that part done. So now let's look at when h is less than 0. And this is quite similar to case 2 now. So we'll define the partition p in that exact same way, but the interval is now c plus h to c, because h is less than 0, giving us the exact same lower mh and capital mh. So then we continue on. We're going to get the exact same inequality we've been having this whole time. Simplifying it down, we're going to get to lower mh times h, which is greater than or equal to that integral there, which is greater than or equal to mh times h. And of course, substituting what we know the integral is, we're going to get this inequality again. And recalling that since h is greater than 0, dividing by h is going to flip the inequality signs. We're going to get lower mh is less than or equal to that fraction there, which is less than or equal to capital mh. Then, of course, squeeze theorem is being applied again. And since we know the limit as h approaches 0 from the left of lower mh is equal to the limit as h approaches 0 from the left of capital mh, which is equal to fc, we get the derivative of capital F at c is equal to fc. Perfect. So what does this mean? So we've shown that the limits from the left and the right are equal. And this implies that the full derivative, so as h approaches 0, that the derivative of f, capital F at c is equal to lower fc. Perfect. So we've proved all three cases. So this tells us that if we let lower f be integrable on the closed interval ab, and define capital F on the same interval, and we define capital F by this expression here, that if lower f is continuous at c is in that interval, then capital F is differentiable at c, giving us the derivative of capital F at c is equal to fc. QED, perfect, and that's all done. So that's the proof. And thank you for watching, and I hope you enjoyed, and I hope it was clear enough what was happening. You should be able to see and pause at certain parts of the video with all the direct steps. I know I said fractions a lot, because I'm not going to sit there and say the exact fractions we're having. But yeah, hopefully you enjoyed, and yeah, I'll see you around.